I do appreciate your coming out on this warm evening. If there is an empty chair next to you and you're not saving it for someone else, could you please raise your hand? Okay, so we do have some seating here in the front. And if you would like a seat, please take it. Let me make sure that my little doohickey here works. So can I, there we go, there was an arrow. There we go. So as Andrea was saying, Western Governors University is a completely online, well, almost completely online university. I teach science teachers. So if you ever wondered if your middle school or high school teacher had to go to school, the answer is yes. And I get to be their teacher. And when I say mostly online, all of my stuff is online, but they have to actually come into a real school and teach and pass tests before they get to be your teacher. So it's like becoming a doctor or a lawyer. You have to do all this stuff. So that's what I get to do in the School of Education. Let me see if I can change this from being, whoops, I obviously did something wrong. There we go, I got it. Okay, so let me advance, because today is Juneteenth. I am so happy that you know what that is, and I'm excited about it. It's one of my favorite holidays because independence and freedom are so important. Can anybody tell me when was the Declaration of Independence signed? There you go, July 4th, 1776. Thank you to whoever shouted that out in the bathroom. And so this gentleman here, named Frederick Douglass, had a question back in 1852. What to the slave is the 4th of July? Because it's really different when you don't have freedom and everybody around you is celebrating and you're the one bringing all the food and the drinks and cleaning up the mess, and that's not cool. So in 1852, he gave this amazing speech in Rochester, New York, and now it is in many schools required reading. If you are not required, I do recommend you read it because it's amazing. So within 12 years, he became an advisor to President Abraham Lincoln, who during the U.S. Civil War declared the Emancipation Proclamation. What is emancipation? That is freedom or liberation from slavery, except not everybody heard the news. Because, well, for one thing, there wasn't any TV, there was no Wi-Fi, there were no computers or cell phones, but also there were people who didn't want the slaves to know that they'd been freed. So the news took a while to spread. It took 2.5 years until 2 months after this U.S. Civil War was over. And then the very last people in Galveston, Texas realized they were free, and they learned that on June 19, 1865. And certain American communities have been celebrating that ever since. I grew up learning about Juneteenth. You know who taught me? My lunch ladies. If you ever went to a school where people in the cafeteria would serve you food, those ladies at my school were part of the civil rights lunch counter sit-ins. They were 13 and 14 and 15-year-olds, and they were risking their freedom. And I was so grateful to learn about this history from them. So yes, now it's a federal holiday. You'll get a day off from work and school, and everybody gets to celebrate. So this is a great run-up to the 4th of July. Enjoy our Well, we also have a couple holidays coming up. We have the summer solstice. And happy Father's Day to anyone who is a father or a fatherly figure or someone who has a father that you want to celebrate. It's basically just a day to recognize people who are awesome caregivers. So why don't you have a round of applause for the person in your life who's can you success stand up because now I have an activity for you. So I did ask some younger members, so Mac and Kaden and Addison and Presley and Eloise and I don't remember her name, Bella, and everybody else who's under age 12. If you are 12 or younger, can you please come up here? 12 or younger, come on up. And while everyone is coming up, let me tell the people who are 13 and older, let me remind the people who are 13 and older that as you are willing and able, you are welcome to stand up right where you are and do this as well. So we're going to have the young people demonstrate for you. But if you want to engage, get up, do a little movement, I'm good with that. I am going to ask Mark to hold this for a moment, because I need the extra hand. And here's what I want everyone to do. So, I'm wearing a bright outfit. I'm going to pretend to be the sun. Okay, so you guys are going to orbit around me. So can you please make a circle around me? Okay, some of you have to be behind me, some of you to the side, some of you to that side, some of you in front. Okay, now for everyone else, you're going to use the projector on the ceiling. Do you see the projector on the ceiling? Yeah. You're going to pretend that that is the North Star. So you're going to put your hands over your head like this. And that is your North Pole. The top of your head with your hands pointing, that's your North Pole. So you got to point it to the projector, which means you rearranges yourself. Now, here's what you got to do. We, on Earth, have a 23.5 degrees tilt. So you got to tilt backward, or to the side. And we rotate. We do one spin around our spin axis. Everybody? But you gotta keep the tilt going. Can you keep the tilt? Now, here's the fun part. Okay, take a moment so you're not dizzy. Take a moment to breathe. Take a moment to breathe. Because you have to assume that position and then orbit around the sun. Can you do that? All right, I'm going to stand really, really still, and you guys are going to go around me. Hands above your head. Make the tilt. Go around me. This way. This way. This, you gotta spin and orbit. This is what our planets and all right. So imagine doing that literally 24/7. And this is why we have seasons. Because when your North Pole is pointed toward the sun, like we're about to have at the summer solstice, here's my so there it is. The June solstice is coming up in 2 days, June 21st. And that's it. Earth's North Pole is pointed toward the sun. It's hot. Now, does anybody know when is Earth as far away from the sun as we ever get through the year? There's a day when we're closest to the sun and a day when we're furthest away. When are we furthest away? What do you think? It's not winter solstice, but that's a good guess. Anybody?
The summer solstice.
It's close to the summer solstice. What do you say? It is not, but that's good. Presley, what do you say, Kaden? Oh, no? Addison? No? You guys are in the wrong part of the year. What do you say? It is July 4th weekend. Are you guys cold on the 4th of July? But that's when the sun and the earth are as far away from each other as they ever get. So distance from the sun has nothing to do with seasons. It's just your tilt. And the more intense the tilt, the more intense the seasons. Anybody have questions about that? Okay, so I've got one more weird thing. It turns out that the summer solstice this year is 5 hours and 42 minutes later than the one last year. Is that kind of weird? Wouldn't it be the same time every year? Okay, all right. No, you're okay with it being different? Why?
Because it doesn't have to always be the same. Like, sometimes.
Very good. It really, the dates and the times really do move around a little bit. So round of applause, because that was a good answer. And did you notice when everybody was orbiting around me, we kind of had a cluster, we had some asteroid collisions? Okay. Well, in real life, those are called perturbations. When you have gravitationally massive objects, and every single one of you is a gravitationally massive object, you have a little pull or tug on everybody around you, even if you're not touching them. Especially, parents know you're always bonded to your kids, and if they need you, you feel it, you're there. So in our solar system, our moon is small compared to Earth, but it's really close. And as a result, it's got a big pull. But so is Jupiter, so is Saturn, so is everything. And so all those pulls and tugs, Earth isn't always in the same place at the same time. So we're off by a few hours each year. So yeah, you gotta check a calendar on your phone app to find out when is the solstice and is it different. My favorite site is this one, timeanddate.com, and it's free, so they've got lots of good info. Anything else before I move on? Can you guys hear me in the back okay?
Yes.
Good, because I'm not doing my usual teacher bubble. I do have teacher voice. I will use it if needed. Okay. And that's up to you, Mark, if that's a threat. Okay, so what we're going to talk about is how life on Earth got here. And that's actually a question that's really been confusing people for a long time. I mean, obviously, there are religious answers and cultural answers and spiritual answers, but we're here to talk about science. And the science is not settled. Science is not just memorizing facts or mathematical figures or diagrams. That's not what science is. Science is a way of thinking about the universe around us, a way of exploring and discovering and innovating new ways of thinking. So it's actually an area of very active debate. How we got life on Earth. Was it brought to us by other things? That idea is called panspermia. Or did the molecules develop on Earth by themselves? Well, this paper, hold on, I'll get to you in just a moment. This paper was published in December, and they said, actually, you can get a molecule like RNA, which is essential for life on Earth. You don't need to bring it from someplace else. And then someone else immediately wrote a paper and said, nah, that's good. What were you going to say? Okay, so if you don't know the answer to this scientifically, that's okay, because neither do the scientists. They're still arguing with each other. And Andrea, you've been, and Pablo, professional scientists, do they argue at conferences or online?
All the time.
All the time. Pablo, you have a comment on
All
that?
the time.
Whatever she says.
Okay. That's a married scientist. Okay, so I thought if Joe will help us, we would actually talk about what life is. So Joe, can you help us out here? Nope, not that one. That one. If you've never done Amoeba Sisters, it is so much fun. Before the Bell Biology has some questions that a teacher can use before class really starts. So Joe,
ready?
if you'll get us started, We're gonna have the audience shout out the answer. Can you hear it? Okay, so which of these is not a general characteristic of all living things? Response to stimuli, locomotion, metabolism, growth and development, or reproduction. And if you don't know what those words are, you will learn it. So you're saying locomotion?
Yeah.
Okay. Joe, can you speed it up so we can see the answer? Yeah, locomotion means to move from place to place, and there are many living things that do not do this. Everything else is required for life. All right, let's see if we can get to the next question. If a single-celled bacterium splits into two cells, this is a direct example of which characteristic of life. I really can't tell what you're saying. Give me the word. Okay, instead of the letter, give me the word. That's why. Yes, reproduction. This gives you a new organism. Okay, Joe, let's go to the next one. When a cactus in a windowsill bends toward the light, this is a direct example of what? All right, Joe, that's the answer. All right, you're correct. We have some science geniuses here. You guys are getting A's in your science classes. Here we go. Okay, last one, number 4. Last one. With the modern cell tree, organisms are multicellular or contain All right, Joe, let's have the answer. Yes, organisms are made of one or more cells. Excellent. Well, I think we are done with this because you know your biology. So thank you very much, Joe. A round of applause for Joe. You guys really know your stuff. I'm very impressed. See, the young folks in our communities, you're teaching them well. Okay, let's go to, I can go to the next slide. There we go. So, Andrea was talking about meteorites. This is a picture of the Murchison meteorite that landed in 1969, the same year as the Apollo astronauts landed on the moon. This landed on Earth, and scientists were able to figure out that, oh my gosh, it has biomolecules, molecules that are needed for biological organisms. And not just like one or two, that whole list that you can see on that slide. And certain kinds of acids are needed to make sugars. Certain kinds of amino acids make proteins. And if you guys are on a high protein diet, like maybe those keto diets, you know protein is really important. You can even get Cheerios with protein added, right? Yeah, and it helps build muscle, right? So the fact that these molecules are pretty easy to make was really a surprise, because they thought they were complicated to make. Well, it turns out that there are sugars just hanging out in interstellar space. There are simple sugars everywhere. And so then the question is, well, we need sugar on Earth, and this is why a plant does photosynthesis to make glucose, the very simplest sugar. And if glucose can power an entire ecosystem on Earth, what is it doing in space? So scientists have detected these bioessential sugars, including one called ribose. And RNA is ribonucleic acid. So ribose, do you see the connection? Yeah, so it's like, wow, is there RNA in space? Well, we're gonna get to that. So I love this. Jason Dworkin at NASA Goddard says, it's got to be harder than just mixing the chemicals together. Otherwise, life would have formed on Asteroid Bennu or anyplace else. Bennu is a pantry full of ingredients, but it wasn't it wasn't quite the right connections to make a cake. On Earth, we have cake, but we don't know why. And by the way, good reminder, it's still Pride Month. Who would enjoy? Yes. All right. So we have life on Earth. We don't really get why. There are life-forming molecules in space. The chemistry works, but we don't know how you get from one to the other. So this is how you make one of these molecules out in space. And we're just going to look at the one on the left where you have things like water. I'm trying to get my little cursor. Here it is. So you have water, and it's probably water ice. You have methanol, which is a kind of alcohol. You have ammonia. If you guys ever smelled ammonia, like in your kitchen, you might have, or in your garage, that stinky ammonia. That it occurs really easily because ammonia is just one nitrogen or three hydrogens, super easy to make. So you get those together and then you cook them with a little bit of ultraviolet light. Remember, the light from a star has all the colors of the rainbow, plus all the colors you do not see with your eyes. But those colors of ultraviolet and X-ray and gamma are on the other side of the spectrum. You've got infrared, microwave, X-ray, radio. All of these colors are still colors of sunlight. We just don't see them with our eyes. But they're still doing what light does. Light and the heat provide energy, and that's enough energy to pull apart the water and the ammonia and rearrange those atoms to make a sugar like ribose, and maybe a more complex molecule like RNA. So how are we going to investigate this? We send sample return missions. These are robot spacecraft. They go to a particular asteroid or comet nucleus or wherever else we're sending it. They have it land on the surface, grab a little bit of the material from the surface, seal it up inside so it's safe, and then bring it back to Earth. And if that sounds really hard, it is incredibly hard. It takes decades to plan the mission, years to actually implement the mission, and then years to analyze the data if the sample comes back safely. And sometimes they crash and you cannot get it back safely. But in this case, with Asteroid Bennu, we were able to get the samples back safely. And what's really neat about Bennu, and we're going to look at a picture, another picture of Bennu in a minute. It's what's called a rubble pile asteroid. Or what's rubble, other than Barney Rubble's last name? What is rubble?
Piles of rocks.
Yeah, piles of just junk. It could be dust. They could be pebbles the size of your thumbnail. They don't have to be big rocks, although you can have big boulders. And if they're all flying together, they look like they're solid, but they're not. It's like a pillow that's filled with feathers. You think you've got one pillow, but really you've got 1,800 feathers. They're just all together, moving the same way. Does that make sense?
Yes.
Okay. So what's really interesting about Bennu is that, well, for one thing, it's got this neat shape. Remember you did the whole, you gotta spin around and tilt? The faster you go, the more you get that central bulge. And the central bulge. This equatorial bulge. So if it kind of looks like an 8-sided dice and it's bulging out, I think that's because of the way it's rotating and the speed. If it goes too fast, it's going to fly apart. If it goes too slowly, it's not going to hold together this nicely. So it's got to kind of like a Goldilocks situation. It's got to be just right. So some of the materials in Bennu are older than others. And we don't know where they all come from. They might all come from a parent body, just like people in your family may have the same mom and dad. But if you have a blended family, that's not always the case. You may have a different dad or a different mom, or you may have cousins living with you. And an asteroid like Bennu is the same thing. It's a family. They're all together, but they may have different parent bodies. You okay with that? Okay. Here we go. So here's another one. This is an asteroid Ryugu. And look how it's spinning. And it's got that same central bulge. But notice how the top and the bottom of this one looks different. So these are a whole category of asteroids, these rubble pile asteroids. And Ryugu was visited by a spacecraft as well. This was a Japanese spacecraft with a JAXA mission. And as I highlighted, all of the 5 nucleobases, amino acids that we associate with life on Earth were found in Ryugu as well. So it's not just Bennu, it's not just one place, now we're seeing it in lots of different places. Well, we don't have too many sample returns, but we have meteorites that have come to Earth. As Andrea explained, my training is as a meteorite researcher. So yeah, we've got thousands of meteorites that have come from other parts of our solar system here to Earth. They've all been studied. And now we can send spacecraft to these places and see them directly. And when you put all that together, you realize there are the building blocks of life on asteroids. There are lots of different things. There are molecules like glycine. There are lyses. Some of you, I notice, are drinking some nice cool frozen drinks. Think of where that ice comes from. It's probably you made it in your freezer, or Starbucks made it in their freezer. But you can have ice naturally occurring on Earth, off Earth, and those ices are made of different molecules. So ice is not just water ice, and you can find all of these really ancient, what are called primordial ices, in all sorts of interesting places in our solar system. Well, of course, if 2 particles that are full of ice hit each other, sometimes you collide and bounce off. Sometimes they collide and stick together. And the heat and force of that impact might be enough to melt the ice. And if you melt the ice, you may have water or some other fluid, and that is going to provide a really nice place to cook up a more complex molecule, like an acid, a glutamic acid, or some other kind of acid that we associate with life. Okay, this is where I get lost because I'm not a chemist. So I put this in here for all of the science nerds and chemistry types. But it just goes to show that in space, just with natural collisions, just with things ramming into each other, you can get a whole lot of chemistry. Just with stuff hanging out there in a nebula, which is a cloud of dust and gas, you can get enough energy to have a lot of sophisticated chemistry and physics. Our solar system is a dynamic place. Everything's moving around. And because they move around and they're interacting with each other, they're doing stuff. They're making things. So are they making molecules? Well, I don't know. Yes, they are making molecules. Are they making molecules and then bringing it to Earth? That's what we still have to figure out. So, how do you make an asteroid like Bennu? Well, get all of your pieces of dust and gas and ice, and then get them wet, and have them get their chemistry going. Make things like salt, including the salt you have in your kitchen. Right? Salt is a whole category. There's some salts that are safe to eat, and some that are not so good to eat. So just if somebody offers you some salt, doesn't mean you should eat it. And once you heat that up, then you can start making stuff that NASA and JAXA and the European Space Agency and other scientists are interested in. And they're gonna write a whole bunch of papers about how salty water which is known as brine. Has anybody ever brined your own pickles? Or watermelon rind? Brine is brine. It's just salty water. And that can naturally occur in our solar system. Here we have a NASA mission investigator holding one of those carbon-rich meteorites that has those amino acids in it. She's got all the building blocks of life in her hand. I know, it's so cool. So the question is, what happens if one of those things hits Earth? And some research was done 15, 20 years ago where, one of those meteorites, one of those carbon-rich ones, if it hits Earth or another planet, there's enough energy so that those amino acids can make those proteins. Once you get protein chains, you can get life potentially. We haven't done it yet in the lab. We have not been able to do it ourselves, but we certainly know that it's possible. So this idea of did life develop elsewhere in the solar system and then come to Earth? Well, I don't know if the life itself could have survived the journey, but what about those building blocks of life, like RNA or DNA? Since they naturally occur, maybe the building blocks came to Earth and then they got assembled here. Think about baking your cake. Remember that cool cake we saw? Yeah. Well, you buy the ingredients in a store, but you make the cake yourself at home, right? I mean, putting in the food coloring and making the frosting is sometimes your best plan. Oh, you're gonna learn that, Elise. It's okay. You'll get it. All right, so Joe, can you please play this video starting at 8:51? And we're gonna end at 10:15. So just a little bit of difference. There we go. Thank you.
So we found ribose in Bennu's now. Really important function. Ribose is an important component of RNA as the sugar phosphate backbone. RNA, some have argued, was actually the first genetic material that started in the origin of life. It's called the RNA world hypothesis. And then DNA, the protein world, followed subsequently. One of the interesting findings actually with the Bennu samples isn't what we found, but what we did find. We didn't find the oxyribose, which is the equivalent sugar in DNA. It forms the DNA. The oxyribose, we didn't see it above our detection limits, but ribose was present. So I think this supports this idea that maybe RNA did come first because there was more ribose available as its building block very early on. And perhaps DNA and deoxyribose did come later on from biological evolution. Some people consider the origin of life just a simple nucleic acid like RNA that could make copies of itself and transfer information that way. Didn't even require DNA or proteins or even a cell membrane. So this discovery of ribose, in fact, is really important and adds more credibility to that hypothesis that maybe the origin of life was just a single strand of RNA. One of the goals of the ORAX mission was actually...
You can stop that now. Thank you. Thank you. All right. So that was Dr. Daniel Glavin of NASA Goddard explaining. And while we're getting set up, does anybody have questions or comments? We're almost done. Yeah, go ahead.
Could RNA have started on this planet, or does it have to come from elsewhere?
That is an excellent question. I'm going to recap it for the people in the back of the room. Does RNA have to come from someplace else to Earth, or could it develop all by itself on Earth? And that is the question that my first slide that talked about this topic was about. We don't know. It's probably both. And actually, let me just get to that, and then we're going to show the video. Yeah, it's probably both, to be perfectly honest, because if it's really easy to make out of space, why wouldn't we have life develop independently on Earth? But that's the thing about cake. Cake is delicious. And there isn't just one place you eat cake. And there isn't just one way. I mean, you can have a cupcake. You can have a gluten-free cake. There are so many ways to have cake. So enjoy the diversity of cake. So I don't really have a definitive answer because we don't have it figured out yet. But yeah, that seems to be the case. There's cake everywhere, or at least the stuff to make cake. But remember, the best tasting cake probably comes from a family member, like mom or granddad. They make the best cakes. But you can also get delicious cakes in other places with ingredients you've never heard of and styles you've never seen before. Those are delicious too. Has anybody ever had a purple ube bowl? Yeah, ube is really bright purple. If you're into BTS, you know that shade of purple. Okay, so if you could please show this video, Joe. We're just going to do the first 3 minutes because then they talk about jazz music, which is nice, but not really.
Now, I know you're a planetary astrobiologist, and this is not planetary because I'm going to talk about an asteroid. But I just read about some of the findings from Bennu, and one of it was, I think that they found 14 amino acids and RNA, and we know that those are building block proteins of life.
So we're on the same page.
Yes.
Bennu is an asteroid that's the size of the Empire State Building.
Okay.
It is on a collision course. Well, it has an orbit that crosses Earth orbit. His next close approach will be in 2182.
Right.
We went there, was the mission Osiris. It was a touch and go.
Yes.
Grabbed some of the material
And came back.
and deposited it back here on Earth.
That's badass.
And we analyzed it and lead into what you just described.
That's badass.
Pick it up and listen.
So what I want to say to you as a planetary astrobiologist is, what are these implications of finding these building block proteins of life? Does it just mean that that stuff is in our solar system and no big deal? Or does it mean that, you know, the likelihood of life is more likely someplace else? What does it mean?
It's really profound. They didn't find proteins, they didn't find RNA, but what they found was all of the stuff you need to make proteins and RNA. The amino acids that make proteins, the nucleotide bases that make RNA and DNA, and they found sugars now too. And that's all the basic stuff you need for life.
Well, what kind of sugar did they find?
I'm down to know.
A couple of different sugars. I'm not remembering which ones. I think ribose was one of them.
It was, absolutely.
Yeah.
It absolutely was.
And these are molecules that got built in and part of the chemical energy where you can set stuff into motion if you want to have some serious chemical action.
Very nice.
Yeah.
So there's a couple of really amazing implications. One is, I mean, remember this asteroid Bennu was just kind of chosen because, as Neil said, it's coming close to Earth, but it's also convenient to get to. So there's nothing about it that's different from like thousands of other carbonaceous, primitive, carbon-rich asteroids out there. But it happens to be full of the stuff of life. What this implies is that when the planets were young, they were all being sprinkled with the ingredients for life, not just Earth, but all of them were being plastered with this stuff that's sort of like the kit, you know, the recipe, just add water, you know, and it implies not just our own solar system, but probably elsewhere. I mean, again, you know, we have to extrapolate, but there's nothing that we know about the chemistry of our asteroid belt that's probably different from that around other stars. And so it implies that the stuff of life is all over young planets in the universe when they've just formed. But the other weird thing is you can ask, so why didn't it progress to life in this asteroid? Why don't you have proteins and RNA? You have the kit, but the kit has not been assembled there. So it also tells you something about that the progress of those materials towards life is not inevitable in every environment. You need the right environment, but the stuff is everywhere.
You have the kid, but not the glue.
Right.
So, David, let me ask you something just completely.
Let's stop it here. Thank you. And that was Dr. David Grinspoon, a very famous planetary scientist, being interviewed by Chuck Nice and Neil deGrasse Tyson. Okay, so that is where I think I'm going to end things, and I want to thank you because you're about to ask me a bunch of questions, and I will do my best to answer them. And if other people know the answers, feel free to shout that out. I'll even give you the microphone. So, any questions?
What is school like?
What is school like? Okay, you're talking to someone who did leave school. I did. I really had a real life. And then I went back and became a faculty member at a university, actually several. So to me, school is fun because school is where you learn lots of things and where the people around you also are learning things. And they're different things. So when you talk to each other and you compare your notes and what you learned in first period versus what they learned in second period, you can start to exchange ideas and get new insights and start to make new connections. So that's what I think school is. Yes.
How are asteroids named?
I'm sorry?
How do they name asteroids?
Oh, how do they name the asteroids? That's a great question. It depends where and when. So until about 50 years ago, remember 50 years ago was right around when the Apollo astronauts were landing on the moon. So before then, we had classically named asteroids and other solar system bodies. And by classical, I mean there really was this approach of you should name something after a deity or a person named in one of the stories from ancient Greece or ancient Rome. And this is how we get some of the names like Jupiter, which is a Jovian planet. Jupiter was also known as Jove. So that was all classical. But if you look over at this wall, this beautiful wall that the volunteers at Little Thompson Observatory made, notice these are Lakota constellations. And all of these objects have Lakota names. So different cultures have different names for the things that they could see with their eyes. So the stars, the galaxies, they were just bright points of light, but they all got specific names and stories attached to them. Every culture of humans on this planet has a different story and different names. Think about all the names you have. You have the name that your parents gave you, but that may be different than how you name yourself. You may be called mom or dad or son or daughter or brother-in-law, right? So you got that name. You may have the title you have at work or at school. So names are tricky things. Well, around 50 years ago, we started discovering so many objects that we started naming them after each other. So I don't know if you know the rock group Queen, but I'm a big fan of Queen and Dr. Brian May, who got his Ph.D. In astrophysics after he did 20 years with Queen. He went back to school and got his Ph.D. So there's asteroid Brian May. There's an asteroid Mr. Rogers. Yeah. So the 60s and 70s and 80s was a great time for that. Well, now we've been discovering so many things that we are naming so fast we can't name them all. So they just have letter and number codes. So we think there are about 1 million objects in orbit around our sun. They don't all have names, but we're working on it. Yes.
Isn't there some international organization that names things?
Yes, but they're very slow and annoying. They are and I believe it's the IAU, the International Astronomical Union, and they got yelled at so badly after they named the first 5 dwarf planets that they didn't meet again to talk about naming all the other dwarf planets. There are like 50 or 60 other dwarf planets, like Pluto and Eris, that we have identified, but these guys refuse to meet and give them names. So I'm mad. But that was a good question. Yes, Katie. A constellation is actually an optical illusion. It looks like these stars or other things are really close to each other, but really it's 3-dimensional. They're far away from each other. It's actually 4-dimensional because we have to include time. Something that was really bright and we're just getting the light now. Well, technically, already have burned out. Think of a light bulb in your own house where the light bulb burned out, and you didn't know it, because the last time you looked at it, it was still bright. So constellations are things in the sky that to us look like they're together, and we can tell a story about them, because stories are so much fun, but they're not necessarily connected to each other. That was a good question. Anything else? Yeah.
Tell us about when you worked at Antarctica.
I may have to come back to that topic again, but I still have my slides. It was long enough ago that I actually made film on slides. Okay, so this is.
I have a theme for next year.
Okay, I'll ask an easier question.
No. I'll think of the other question, but let me quickly answer that. I spent 10 weeks in Antarctica. I got to work with the U.S. Navy, and they actually gave me an award for doing that. So I have the U.S. Antarctica Medal from the U.S. Navy. And my team collected, oh gosh, I can't remember the number now. It was hundreds. We had NASA issued Ziploc bags and duct tape, and we had to use our NASA issue scissors to cut the bags and seal them with duct tape because we were going to run out of bags. That's how many asteroids we collected. And some of them were pieces of asteroids, just like we were talking about tonight. In fact, most meteorites are leftovers from the formation of the solar system. So they don't always get into bodies like asteroids and comets. So it was a full spectrum. Okay, Addison. There were pieces of them because they all have to go through Earth's atmosphere, and you burn up and you lose a lot of material. When you see that meteor streaking through the sky, that's actually the object from space burning up and losing its outer layers. So whatever survives to the ground, most of them don't. But the ones that land right where you can pick it up, those are the meteorites. Okay, did you have a follow-up question?
Just to ask you how you find it.
Believe it or not, you have a search pattern and you walk. Or if you have a long distance and worth it meteorite here. Or you can use bicycles. Again, you want to go slowly because you want to look at what's on the ground. In Antarctica, we use snowmobiles and we did a search pattern. Okay, Presley.
Based on the meteorite, without based on
Okay, so the question is, based on the meteorites we found, could you figure out how old they are? And the answer is yes. When you do something called radiometric age dating, which takes isotopes of certain atoms, like carbon-14. Have you guys heard of carbon-14 age dating? Some of you are saying yes, some don't. There are other isotopes that are really good for identifying the ages of different things. And so that analysis is done by NASA or some other organization. Everything in our solar system, with a couple of exceptions, tends to be about 4.5 billion years old. So that's how old our solar system is. 4.5 billion with a B years old. Some things like our own moon are a little newer, but most things are about that age. Okay, did you have a question? Kaden.
Where do meteorites form?
Where do meteorites form? Remember I mentioned that nebula, that cloud of dust and gas just hanging out there in space making sugar? Yeah. So when you have a gamma ray burst, or when you have a supernova explosion, some of that energy or material can make that cloud of dust and gas spin. And when it spins, it will start to clump. It will start to gather material. And it flattens into a pancake shape that we call an accretion disk. And then we get more clumping, kind of like dust bunnies under the bed. Have you noticed there's some places you get these big dust bunnies and others you don't get anything? That is very similar to how solar systems form. You have gravitational forces pulling things together, electrostatic forces making them stick, and before you know it, you got a solar system. And I know, Andrea, you have more to say on that topic. Would you like to?
then that is what swirled and came together, forming our solar system. And our solar system is actually made of atoms and molecules that were formed earlier by previous stars. So our sun, our solar system, and us all came out of previous stars, where the center of the star, through hydrogen coming together and the nuclei forming bigger atoms, then into helium and the carbon in our bodies, the oxygen that we're breathing right now. All of those larger atoms were forged in the center of previous stars. And we are a second or maybe third generation solar system. And so if you've ever heard the phrase that we are made of star stuff, that is because the atoms that part of our carbon-based life, the oxygen that we're breathing right now, those atoms formed in the center of previous stars. And we are literally made of star stuff.